Previously, we've explored what a Taylor polynomial is and how they are constructed. We're going to use that construction now to look at 4 different examples. Let's start off with a reminder of what a Taylor polynomial is. So the nth order Taylor polynomial, which we're going to call p sub n of x, we're going to use that to approximate a function f of x centered at x equals a. That's going to be given by the sum from k equals 0 to n of the kth derivative of f at a divided by k factorial, all times x minus a raised to the k power. All right, in our first example, we are going to approximate the function f of x equals ln x. We're going to center our approximation at x equals 1. And we're going to construct a second degree Taylor polynomial, so p sub 2 of x. So in general, p2 is going to be f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. So let's make a list of the derivatives we need. F prime of x is 1 over x, and f double prime of x is then negative 1 over x squared. F prime of our a value is going to be f prime of 1 is 1, and f double prime of 1 is negative 1. And also notice that f of 1 is the natural log of 1, which we know is 0. So if we build our polynomial p2 of x, we get f of a is 0 plus f prime of 1 is 1 times x minus a is 1, plus f double prime of a over 2, so then we have minus 1/2 times x minus 1 squared. And now we're going to use that to approximate the natural log of 1.2. So we want to estimate f of 1.2, and we know that's approximately the same as p2 of 1.2, which is going to be 1 times 1.2 minus 1, minus 1/2 times 1.2 minus 1 squared. And if we tidy that up, we get 0.2 minus 1/2 times 0.2 squared, which is 2/10 minus 1/2 times 4 over 100, which gives us 2/10 minus 2 over 100, which is not 4, 20 over 100, minus 2 over 100, which is 18 over 100, or 0.18. Now notice, if you do this on your calculator, the natural log of 1.2 is going to actually equal 0.1823, and it keeps going, but we're pretty darn close with our second degree polynomial approximation. All right, this time we're going to construct a fourth degree polynomial, and we're going to use that to approximate the sine function. So let's just remember, in general, p sub 4 of x is going to be f of a, f prime of a times x minus a, the second derivative divided by, oops, that's at a, not at x, divided by 2 factorial times x minus a squared, the third derivative at a divided by 3 factorial times x minus a cubed, and then the fourth derivative at a over 4 factorial times x minus a to the fourth. So our function is sine x. Our a value is pi. So let's calculate some derivatives. F prime of x is the cosine of x. F double prime of x is negative sine x. F, the third derivative, is going to be negative cosine of x. And the fourth derivative is going to be back to positive sine of x. So f of pi is the sine of pi, which is 0. F prime of pi is the cosine of pi, which is negative 1. F double prime of pi is the negative sine of pi, but that's still 0. The third derivative evaluated at pi is negative cosine of pi, that's positive 1. And then the fourth derivative at pi is back to 0. So our polynomial looks like p sub 4 of x is going to be f of a is 0. Then f prime, we get negative 1 times x minus a, which is pi. And then plus 0 for the second derivative. Then the third derivative is plus 1 over 3 factorial. 3 factorial is 6. And we get x minus pi cubed. And then the fourth derivative is back to 0. So if we simplify all that, we see that our fourth order Taylor polynomial is negative 1 times x minus pi plus 1/6 times x minus pi cubed. And we can use that to approximate the sign of values that are near pi. All right, we're going to do another example with an approximation now. We want the third degree polynomial, so p sub 3 of x, for f of x equals e to the x over 2. We're centering that at a equals 0, and eventually we're going to approximate the square root of e with this. All right, so we know we need 3 derivatives. So we have f of x is e to the x over 2, which means that f of 0 is e to the 0, which is 1. F prime of x is 1/2 e to the x over 2, which means f prime of 0 is 1/2 e to the 0, which is 1/2. The second derivative is going to be 1/4 e to the x over 2. So f double prime of 0 is going to be 1/4. And then our third derivative is going to be 1/8 e to the x over 2, so that f triple prime of 0 is 1/8. All right, so our polynomial looks like f of 0 plus f prime of 0 times x minus a, which is 0, to the first power, plus f double prime of 0, 1/4 over 2 factorial, times x minus 0 squared, plus 1/8 over 3 factorial, times x minus 0 to the third. We'll tidy that up. This is 3 factorial, so we get 1 plus 1/2 x plus 1/4 over 2 factorial is 1/8 x squared, plus 1/8 times 3 factorial is 6, that's 1/48 x cubed. All right, we're going to notice that we want to estimate the square root of e, but of course that's equal to e to the 1/2. Our function is f of x equals e to the x over 2, so e to the 1/2 is f of 1. So we're looking to estimate f of 1 using p sub 3 of 1, which is going to be 1 plus 1/2 plus 1/8 plus 1 over 48. So that's 48 over 48 plus 24 over 48 plus 6 over 48 plus 1 over 48, which gives us 79 over 48, which is approximately 1.645 1.58. Now we can do on the calculator, the square root of e is 1.6487. So we can see once again that our approximation is pretty close to the actual value. All right, we've got one more example. We're going to estimate f of x equals 1 over x, centered at a equals 2. We're going to look for P3 of x, the third order Taylor polynomial, and eventually we will approximate f of 2.2 to estimate 1 over 2.2. So we know that f of x is 1 over x, which means that f of 2, 1 over x, is 1/2. F prime of x is going to be negative 1 over x squared, so that f prime of 2 is negative 1/4. F double prime of x is going to be positive 2 over x cubed, so that f prime of 2 is 2 over 8, which is positive 1/4. And then f triple prime of x is going to be negative 6 over x to the 4th, so that I forgot a prime up here, f triple prime of 2 is negative 6 over 16, which is negative 3/8. All right, we're going to use those values now in order to calculate P sub 3. So P sub 3 of x is going to be f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 over 2 factorial times x minus 2 squared plus, in this case minus since it's negative, f triple prime of 2 over 3 factorial times x minus 2 cubed. And we can tidy that up a little bit. So we'll get 1/2 minus 1/4 times x minus 2 plus 1/8 times x minus 2 squared minus 3 over 48, since 3 factorial is 6, times x minus 2 cubed. We'll use that to evaluate or to estimate f of 2.2. So we'll plug 2.2 in, and we're going to get 1/2 minus 1/4 times 2.2 times, or 2.2 minus 2 is 2/10. I'm going to use fractions here because they're a little easier for my brain to work with. 1/8, and then I get again 2 minus 2.2, so that's 2/10 squared, and then minus 3 over 48 times 2/10 cubed. All right, writing all of that out, we have 1/2 minus 1/20 plus, that's 4 over 100 times 1/8, so that's 1 over 200. And then in the last, we get 3 times 8 is 24 over 48 times 1,000 times 1,000. So that becomes 1/2 minus 1/20 plus 1 over 200 minus 1 over 2,000. That's 1,000 over 2,000 minus 100 over 2,000 plus 10 over 2,000 minus 1 over 2,000, which gives us 909 over 2,000. 909 over 2,000 is 0.4545. But 1 divided by 2.2 is 0.45. Repeating, so we see in this case we get a really accurate estimate for our rational expression. Wrapping things up, what we've seen here is that if we construct the Taylor polynomial, the polynomial so that all of its derivatives through the nth exactly match the function we're attempting to approximate, then we can use that polynomial and get some pretty good approximations for functions that require a calculator generally in order to evaluate them.